let's review these 7 steps before we take up a problem that involves all these steps. The first step is discretization. The second step is selection of approximating function, which leads to form of the algebraic equations for one element. And now this part 2, this step 2, we have already done, and we have the form of the algebraic equations for linear rod element. Step 3, calculation of elemental equations. This is nothing but application of step 2 to all the elements of the system. Number 4, assembly of elemental equations to system equations, and that is done by connectivity table, which was mentioned when we did minimization of potential energy. 5th is application of boundary conditions. Number 6, solution of resulting equations for displacement, and finally calculation of strains and stresses. So this is our problem. A plate of 3 millimeter thickness. The width of the plate is variable. It's linear variation, and we are supposed to solve this for stresses. Since we don't have a tapered bar element, we only have the element with a constant cross section. Let's divide this into 3 equal parts, 3 equal lengths. And let's take the area at the average area at the midpoint of all these elements. So this is what is called approximation. Actually, we are approximating a tapered bar with 3 steps. So obviously what we are going to get is an approximate solution. For simplicity's sake, we are only taking 3 elements, but actually to get accurate result, we must subdivide it into more number of elements. Width of each section is 46 millimeter. Very easy to see that is the case. This is 38 millimeter, and this one is 30 millimeters. The length, because these are of equal lengths, these are all 60 millimeter. The force to 20,000 is there at the end, and let's number these elements and nodes. We have this node here, 2, 3, and there are 4 nodes, 1, 2, 3, 4. Numbering doesn't matter here. Any node numbering will do essentially. There are things to be said about node numberings, but they are more concerning the ease of computation, not about right or wrong. So you'll get the same answer anyway. And the elements, this is element number 1, this is element number 2, this is element number 3. So essentially what we have done is we have converted this system into one, 2, 3 elements and 1, 2, 3, 4 nodes. This is step number 1. Discretization. Step number 2. Step number 2 was selection of approximating function. Recall, or displacement function. Now that we spent quite a while starting from that approximating function to derivation of the form of the algebraic equation for one element. So you don't need to do the step number 2 for all the problems that are given to you. Once you have that in your library, it's just a matter of reading it from there. So if you recall, the K for an element for this kind of a problem is A, E. This E means that element, because we have elements of different areas. So just add E here, and U for an element we call was UI UJ, and F was FI FJ. So because we have three elements, step number 3. Step number 2 is the form of the algebraic equation. Now this, obviously the algebraic equation being this one. So this form is essentially the same for all the FEM problems, but the details, that is this K, this F, these will be different. So in this case, this is step number 2. Step number 3 was the calculation of elemental equations. So we have 3 elements, so we need to have 3 separate sets of calculations. Let's start. It's very simple. It's a matter of a few minutes. K1 is, if you recall, this is 46 millimeter, 38 millimeter, 30 millimeter width, and thickness is 3 millimeters, so that is constant. And the material being steel, it has a Young modulus of 200 GPa. So area for element 1 is 46 into 3, and then you have this Young's modulus converted to MPa. This is the length, 1 minus 1 minus 1 to 1, so you get 46 minus 46 minus 46, 46. Just for simplicity, and is per 4 here, so you don't have to write it again and again everywhere. This incidentally will be in Newton per millimeter, because we are only using Newton millimeter and MPa in our calculations. Now F1 will be, actually this is for element 1, you have node 1 and node 2, there are no forces on node 1 or node 2, so we have 0 and 0. Similarly for element 2 it will be 0 and 0, for element 3 it will be 0 and 20,000. So this is again a matter of reading of the diagram. Now A2, coming to the second, the only difference being here you have the thickness, the width being different, otherwise it's the same thing. The rest is exactly the same, and in this case this is this force is in newtons. F2 again, like discussed earlier, 0 newtons. And finally A3, and in this case this is 30 into 3, again the only difference being the width, the rest is the same. This turns out to be these numbers, and for the first time you have some values in the force vector. Now step 4. Step 4 was the assembly. Again recall the steps. Assembly into system equations. These are elemental equations, all. If I write K1 vector U1 U2 is equal to this 0 0, this is an elemental equation, and the same can be done for the 3, but we have to assemble all these into system equations, and for that we need a connectivity table. It's very simple. All you need to do to construct a connectivity table is look at the diagram and have accounting for nodes and elements. For example, element, nodes. Now in nodes you have I node and j node. So what you get actually is this kind of a table. Now this is a very simple problem, so it's very easy to do, but even for complicated problems, this is not a difficult step. Now this is a very simple problem. So element 1 corresponds to node 1 and 2, element 2 to nodes 2 and 3, and element 3 to nodes 3 and 4. This accounting is very important for all FEM problems. So just write that down here. 1 is node 1 and 2, element 2 node 2 and 3, and element 3 node 3 and 4. So this is your connectivity table. All you need to do here is you have this connectivity table with you, and you have to make the system equation. Now the system equations, one thing we know about the system equations is the degrees of freedom will be 4 in this system. There are only 4 nodes, and each node can only move in the x direction because it's a 1D system. So total degree of freedom 4. So if that is the case, then the K matrix, system K matrix, can also have the dimension 4 into 4. And similarly, the force vector, this also can only have a dimension of 4 into 1. So all you need to do now here is just write this information from the connectivity table to the elemental quantities. Element 1, 1 and 2. So you write 1, 2, 1, 2, similarly 1, 2 here. Element 2, 3, 2 and 3. So you write 2, 3, 2, 3, similarly 2, 3. Element 4, element 3, 3 and 4. 3, 4, 3, 4, 3, 4. And this is for the system matrix and vector. Now what remains is bring these to where they belong in the system matrix. So 1 2 1 2, this position is called 1 1 position, this is called 1 2, this is called 2 1, and this is 2 2. So this becomes 46 minus 46 minus 46 46. Now when we come to the second element, this is shared, this is 2 2 position, this is shared with this 46, so this will be superimposed. So 38 minus 38 minus 38 38. Simply this is the shared part, minus 38 minus 38 38. Similarly, going to the element number 3, now we have 30 minus 30, again this is 3 3 spot, so this is shared here, so 30 will be added here. This is minus 30 minus 30 and 30. The rest is simply 0. Same goes for force. This is 0 and 0. But when it comes to the second element, there is again 0 and 0. To the third element, there is 0 and there is 20,000. So this is your element. This is your system equations. If you simplify, 46 minus 46 minus 46, 84 minus 38 minus 38, 68 minus 30 minus 30, 30, 0, 0, 0. U1, U2, U3, U4, 0, 0, 0, Now let's pause for a moment and look at this stiffness matrix. This one is a system stiffness matrix. There are a few properties of this matrix. First of all, it is a symmetric matrix. Well, let's list them. Symmetric. Secondly, all rows add up to 0. And because it is symmetric, all columns also add up to 0. If your K matrix for a stress analysis problem is not symmetric, or all rows and all columns don't add up to 0, then there's a problem. Go back and check. Now there's some bad news also, and that is the third property of this is that this will always be singular. And by singular, we mean that its determinant is 0. That is, there is no inverse. You cannot invert it. So our goal is to find these the u vector, u1, u2, u3, u4. So because if we have u's, then we can go on to strains and stresses. But for that we need to invert it, which we cannot do. But the good news is that in the next step we'll be able to invert it. And that next step is step number 5. Application of boundary conditions. Now in this problem, we don't know the values of u2, u3 and u4, but one thing is for sure, and that is that the displacement at node 1 is 0, because it is at that point it is fixed to a rigid wall. So u1 is equal to 0. So let me write this again. This was the original equation. Now this is 0. We know that this is, and in all problems, at least one, most probably more nodes, will have some sort of boundary condition. It may not be 0, but it will have some value. And unless you put that value here, your problem will not be, you will not be able to solve the problem. Now this becomes 0 by the application of a force that is applied at the wall. The reaction force. If that reaction force is not there, the force provided by the wall, then this u1 is not 0. This is 0 precisely because the wall puts a reaction force at that point. So when you make this u1 equal to 0, you should add the reason why it is 0. Incidentally, if there is no boundary condition in a problem, you apply forces and nowhere it is constrained anywhere, what happens? The whole thing moves. So it's not a stress analysis problem, it's a dynamic problem. You start getting acceleration, you start moving faster and faster and faster. So you have to, for stress analysis, if you apply a force, you have to constrain the system somewhere. Now in this case, if u1 is equal to 0, then you know that u1 is being multiplied by this first column. All these values are being multiplied by u. So they are not needed for the sake of our calculation. And even the first row for the moment is not needed because we already know u1. So we just ignore this. And what remains is not singular. This is the good news. Matrix that remains after the application of boundary conditions is solvable. You can get the inverse, and so you can calculate the displacements. And here, if I use my Casio 991, our national calculator, I get these results. U2 is equal to 0.0435. You should also check these values. U3 0.0961 millimeter, U4 0.1628 millimeter. And this incidentally is our step number 6. Calculation of displacement values. And add to this U1 is equal to 0 that you already know. This is your step 6. Now, once you know U1 to U4, if needed, you can calculate the value of R1 by using the first equation. And no prizes for guessing that R1 will turn out in this case to be minus 20,000 Newton. It has to be, but in more complicated problems, you can calculate it using the equation. Now, mostly this is not required, but in some cases, for example, beam problems, this may be required. Now we move on to our 7th and final step, calculation of strains and stresses. Now recall the B matrix. What was the B matrix? B matrix was the matrix that linked for an element the nodal displacement values ui uj with the strain values. So, and this was the B matrix. In this case, the B matrix is this one. All we need to do is do it 3 times because we have 3 elements. So for element 1, it is minus 1 over 60, 1 over 60. For element 1, we are talking about nodes 1 and 2, that is ui and uj will be u1 and u2. So this is 0, 0.0435, and this turns out to be 7.25 into 10 raised to power minus 4. Strains have no units. For element 2 again, the lengths are the same. In this problem, we have the same lengths, but generally speaking, lengths need not be the same. So element 2, the nodes are u2 and u3, so the values here will be 0.0961, and this then turns out to be 8.77 into 10 raised to power minus 5. And again, you check these values with your own calculations. Finally, we come to element number 3. Again, the same lengths, and this time we have u3 and u4 0.0961, 0.1628, and the strain in the third element is 1.11 into 10 raised to power minus 3. All that remains now is the calculation of stress, and stress values and strain values are linked with this equation, Young modulus, and so the final step in this case will be sigma 1 will be 200 into 10 raised to power 3, we have to what MPAs into 7.25 into 10 raised to power minus 4, which is 145 megapascals. Sigma 2 again 8.77 into 10 raised to power minus 4. This turns out to be 175.4 megapascals. and finally sigma 3. This is 200 into 10 raised to power 3 into 1.11 into 10 raised to power minus 3. This is 222 MPa. These strains and these stresses are constant in each step. In the case of the tapered bar, that is not the case. The bar is gradually decreasing in width, so the stress should also gradually increase. If you compare the displacements of the two situations, in the case of the tapered bar that was given to us, the displacements are very smooth like this. In our case, because of the discretization into only 3 elements, our displacements take this form. Strains, which are the first derivative of displacement, this is it's a slope, so this keeps on changing everywhere. Strain here is different from strain here, is different from strain here, and this is gradually changing. And stress is proportional to strain, so the stress ought to be changing gradually. But in our case, all through the first element, we have the linear distribution, so the strain must be constant throughout. Constant strain, constant strain, similarly constant strain. And if the strains are constant in the 3, then the stresses will also be constant. So how to mimic the behavior of the actual system, the tapered system, more accurately? So obviously by increasing the number of elements. Let's say instead of only 3, we had 20 elements, then we could have achieved something like all linear. These are all linear, but we could have mimicked the situation much more accurately. In this case, incidentally, we know the exact solution also for this tapered problem, and so we can refine our mesh until we come close to that. But generally speaking, we don't know the exact solution. So what is to be done in that case? In that case, we go for something called convergence, and that is something that we'll discuss later on. Some food for thought. FEM has given us an approximate solution in this case, but if the problem, instead of consisting of a tapered bar, originally consisted of 3 steps, each of constant cross-section area, subjected to some force here, but the same linear rod element have given us an approximate solution or an exact solution, and why? Thank you very much.